Good afternoon, students. I've switched on the main switch and the dimmer is at 0. Now I want to set this dimmer setting to around 30 watt or 35, 40 is okay. So now it is at 30 watt, 29 watt to be precise. So the voltmeter reading is 29 volts and the emitter reading is zero point 0.1 and the temperature T1 is 25, T2 will also be 25, more or less all the temperatures initially will be the same. Like that, you will have T3, T4, T5, T6, T7, T8. So, yeah, T3, now T3, let's see something. Yeah, that's again 25, 25, 25, 25. Yeah, 26. So this is how we started. Follow me carefully. Yeah. So here you have a sphere basically. This is a sphere, and in the sphere you have so many thermocouples. So what you will do, you will switch on the mains at the back, and then you will switch on this one here. Once you switch on this, the dimmer will be at 0. I have set the dimmer to so and so values. Here the emitter reading is 0.1, and as you can see in your video, you can look at these values also. And the voltmeter reading is 29 volts. So it is around 30 watts that you have taken, and the temperature reading is seen in your video. Now at 12:30, I will take probably the next reading. So when we take that reading, we will enter that here and then move on to the calculation. Let me tell you about the construction of this sphere here. What you are seeing here is a sphere, and this sphere is actually having a heater inside it. Okay, there is a spherical heater. This is heater. This is present inside, and the space between these two, the outer shell and the heater, is filled with insulating powder. Okay, that's why you are calling it as insulating powder experiment. And what you want to do is you wanted to find out the thermal conductivity of this insulating powder. So how do you do that? For doing that, you have thermocouples placed here, T1, T2, T3, T4, 5, 6, 7, 8, 9, 10. So these are the positions of the thermocouples, meaning that 1, 2, 3, 4 thermocouples are placed placed on the inner sphere. I can say on the inner sphere 1, 2, 3, 4 are placed, and 5, 6, 7, 8, 9, 10 are placed on outer sphere. So using this data, we have to find out the thermal conductivity of this insulating powder. So we have started the experiment, and we will wait till the steady state is reached. Once the steady state is reached, we can take those readings and put into the appropriate formula here. What is the formula here basically? So when I write Q here, Q is equal to 4 pi k I can take into delta T. T inner minus T outer by 1 by R minus 1 by R. Here this R will be higher, this will be lower, so that the value will be positive. This side will have higher value, this side will have lower value. So how do you get T inner in this particular equation? So Q anyways, you know, Q is V into I, and T inner is the average of T1, T2, T3 and T4. T outer, what it is, it will be the average of T5, T6, T7, T8, T9 and T10. That is inner sphere, these 4 thermocouples are there. Outer sphere, these 6 thermocouples are there. For the corresponding temperature values, you are taking the average with the corresponding thermocouples. So that's how you'll get the temperatures here. And then radius. How do I get the radius? Radius you will get using this one, using your specification board. In specification board, you can see that the outer diameter, outer sphere diameter is 100 mm. Inner sphere outer dia and outer sphere inner dia. So what I can take here is 100 mm and 200 mm. So if I have to represent it here, this inner dia is 100 mm, this 100 mm and this is 200 mm. So if I have to take the R values here, R higher, lower is 100 by 2, which is 50 mm. So you have everything in this particular formula. What you can do is you can simply substitute the values to get K. Okay. If I write K here, it will, this is how you'll get the thermal conductivity. Generally, this thermal conductivity value should be very less, because this is insulating powder. The thermal conductivity possessed by this will be very less. Okay. Now, so this is all about your experiment. Actually, this is very simple experiment. Once you get the steady state readings, you can take the steady state readings and put into these values. Once you put into these values, you are done with your thermal conductivity. It is very simple experiment. Now, let me tell you what are the various things that you should look at. Okay, what is the use of this experiment? See, if you do composite wall experiment, it is a Cartesian coordinate system. Lagged pipe experiment, if you have done, it is a cylindrical coordinate system. Whereas here, it is a spherical coordinate system in this experiment. You have a sphere here. This is a sphere, and this sphere is having temperature variation. And if you take this particular formula, what are the assumptions that are there behind this formula? Okay, see, in this formula, what you have is only with respect to radius, only the temperature is varying. So various assumptions, if I write here, the heat transfer is one dimensional. Okay, and that with respect to r only. If I take the spherical coordinate system, r comma theta comma phi. See, r comma theta comma phi, if you take, theta and phi can be neglected. How can I neglect theta and phi? See, you look at these values. When you look at these values, no, once you get the higher temperature variation, T1 to T4 will have one value, and T5 to T10 will have a different value, meaning that there is a variation with respect to radius. Whereas if you take with respect to T1 and T2 and T3 and T4, they're all same. Okay, with respect to plane, there is no variation. That's why with respect to theta and phi, These two, there is no temperature variation. So with respect to R only, there is a temperature variation. That is one thing. The other thing is here you don't have any chemical reaction happening inside. So Qgen will be equal to 0. This is one more assumption that you can take. And one more thing is it is steady state. Okay, unless there is a steady state, you cannot apply this equation. So all these assumptions should be behind while you use this particular equation, and few more I can take it like Kr is equal to K theta is equal to K phi. Okay, K is not varying with phase coordinate. Okay, that is one thing. And one more thing is K is not varying varying with temperature. So all these assumptions should be kept in mind while you use this equation, this particular equation. Okay, all these things are satisfied in our experiment. That's why we are using this particular formula here. Okay. Mm. One more thing is what are the applications of this? Okay. Somebody asked in the class, what are the applications of this kind of spherical coordinate system? Applications of spherical coordinate system. Okay, spherical coordinate heat transfer I can write. The applications can be like your ball, okay, or air inside football, air in football, your basketball, all those things are spherical coordinate system. You can take spherical tanks where liquid nitrogen is stored. Okay, and then spherical containers would store rather than storing, they carry, which carry molten metal. If you go to a steel plant where the steel is manufactured, there you will have steel at very high temperature of 1500 degrees centigrade. To store that, to carry that from one place to the other place, you will be having a very big wagon, and that wagon is made out of a spherical shape. Okay, if it is made out of spherical shape, you can use this principle to actually design the heat transfer. Okay, there whatever the heat that is there in the molten metal should not come out while you are carrying it from one place to the other place. While you're carrying it, the temperature should be maintained and temperature should not drop. So for that purpose you can use this. And even human eye is also an example spherical coordinate system, wherein if you want to design a contact lens, if you want to design a contact lens for a human eye, you need the principle of this spherical coordinate system. Likewise, you can have so many things. Let us say you are analyzing a potato in boiling water. If you want to analyze this potato, you have to use a spherical coordinate system. Okay, likewise, there can be many examples. Okay, many such examples can be taken. So it's up to you to think. It's your creativity. Let's take the reading. Okay, it's not working. It's 8, 7, it's 6, 5, it's 4, Yeah, you can see them right here. So now you can take these readings and substitute into your expression, because what you can see here is the variation of temperature is not huge. Okay, so with time the temperature got stabilized, and this temperature readings you can take for your steady state. These readings you can take for your steady state, and then you'll get the value of your K. So what I get for T inner here is 168 plus 167 plus 167 plus 168 by, sorry, it's not 2, it's by 4. That's so and so value. And T outer is equal to 32 plus 32 plus 32 plus 32 plus 32 plus 32 by 6. This is again 32 degrees centigrade only. Whereas this will be 167.5 degrees centigrade. So T inner and T outer you have, and that's all. Everything else you have in your expression, you just substitute and get the values. Yes, K value, somebody did it in chart. Yeah, it is 0.017 watt per meter Kelvin. Good. So the K value, if you substitute it there, what you get is K is equal to Q by, Q is V, let me write the Q by 4 pi into 1 by R minus 1 by R. It should be like 1 by 167.5 minus 32. Duke is, yeah, where should I
Units
correct this?
units of degrees centigrade.
Here I have written it correct, but here is, yeah, degree centigrade. Somebody is saying, what is that?
Units, temperature units, degree Celsius.
Yeah, here why did I write Kelvin? Is that your question? Both are same. 0.017 watt per meter degree centigrade. Whether you put it in Kelvin here or in degree centigrade, you will get the same value, because plus
Okay.
273 minus 273 will get cancelled.
Okay.
So value will be the same. The result. So the result is thermal conductivity of insulating powder is found to be found to 3.017 watt per meter Kelvin. Okay. You can also find out the thermal resistance if you want. That can also be done. It can be done like RTH is equal to delta T by Q. It is 167.5 minus 32 by 0.1 into 20. Gets also value in Kelvin or watt. This value will be very high because this value is very less. So in your conclusion, you can write that this material has very less conducting ability and very, thus very high insulating capability, which is C. resistant. Okay, you can write this in your conclusion. Like somebody tell me this value. What is this value?
40, 46.724.
46.724. See, this much resistance is there for the heat to flow. That's why it is not flowing and the thermal conductivity is very less. That is the reason why this can be used as a insulating material. So that's what the point. This thing. So that's all from the experiment side.